Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The dawn of the 20th century found atomic theory ensnared in a paradox. Classical physics, the bedrock of scientific understanding at the time, faltered when confronted with the intricacies of atomic spectra, particularly the elegantly patterned Balmer series for hydrogen. This series, a set of discrete wavelengths of light emitted by hydrogen atoms, stood as an immutable challenge to the continuous, wave-like nature of classical electrodynamics. Attempts to reconcile these observations with existing theory proved futile, leaving physicists grappling with an increasingly evident chasm between the predicted and the observed. Niels Bohr, a young Danish physicist then working in Rutherford's laboratory, dared to bridge this divide with a series of audacious postulates outlined in his groundbreaking 1913 treatise on the constitution of atoms and molecules. Bohr's proposal represented a radical departure from classical electrodynamics, challenging its fundamental tenets in favor of a bold, new vision of atomic structure. Central to Bohr's revolutionary model was the quantization of electron orbits and energy levels, concepts entirely foreign to the classical worldview. He asserted that electrons could only exist in specific, discrete orbits around the nucleus, each corresponding to a distinct energy level. Furthermore, he proposed that spectral lines arose solely from transitions between these allowed energy levels, with the energy difference between the orbits dictating the frequency of the emitted or absorbed radii. Bohr stood upon the shoulders of giants. Ernest Rutherford's nuclear model of the atom, established through his famous gold foil experiment, provided the structural foundation for Bohr's theory. Rutherford's model, while revolutionary in its own right, presented a significant problem. According to classical electrodynamics, electrons orbiting the nucleus should continuously radiate energy spiraling into the nucleus in a fraction of a second, rendering atoms inherently unstable. Max Planck's quantum hypothesis, introduced in 1900 to explain blackbody radiation, offered a crucial intellectual spark. Planck's assertion that energy could only be emitted or absorbed in discrete packets, or quanta, provided a precedent for Bohr's quantization of electron orbits. The work of Johannes Rydberg, who empirically derived a formula describing the wavelengths of spectral lines, provided both inspiration and a critical benchmark for any successful atomic model. Bohr sought to solve two fundamental problems: the inherent instability of Rutherford's atomic model and the discrete nature of atomic spectra. Classical physics predicted the rapid collapse of the atom. In contradiction of this, Bohr introduced his pivotal postulates. First, he posited that electrons could only occupy specific orbits without radiating energy. In these stationary states, electrons defied classical predictions, orbiting the nucleus without losing energy. Second, he asserted that radiation is emitted or absorbed only when an electron jumps discontinuously from one allowed orbit to another. The frequency of the emitted or absorbed radiation is directly proportional to the energy difference between the initial and final orbits. This frequency would align with the observed wavelengths of spectral lines. Bohr's model offered an explanation for the Rydberg formula, a formula that accurately predicted the wavelengths of hydrogen spectral lines. The Rydberg formula, expressed as 1 over the wavelength equals r times 1 over n1 squared minus 1 over n2 squared, where r is the Rydberg constant and n1 and n2 are integers, had previously been an empirical observation. Bohr's model gave it a theoretical foundation. By applying his postulates and utilizing classical mechanics, Bohr successfully derived the Rydberg constant from first principles. This derivation showed remarkable agreement with the experimentally determined value. This achievement provided strong evidence in support of the quantization of electron orbits and energy levels. The immediate impact of Bohr's model lay in its successful quantitative explanation of the hydrogen spectrum. It correctly predicted the wavelengths of the observed spectral lines through the transition of electrons between energy levels. It also envisioned the existence of previously unobserved spectral lines in other regions of the electromagnetic spectrum. Bohr's model provided the first coherent framework for understanding atomic structure and spectra, ushering in a new era of atomic physics. The model offered clarity where previously confusion existed. Bohr made a prediction on the precise positioning of existing spectral lines, achieving a substantial accomplishment. This marked a turning point in the scientific community's understanding of the atom. Its implications resonated far beyond the confines of theoretical physics. Bohr's third postulate represents a revolutionary departure from classical physics, asserting that atoms only emit or absorb radiation when an electron transitions between allowed energy levels. The frequency of the emitted or absorbed radiation, denoted by F, relates directly to the energy difference between the initial energy level, denoted by E sub I, and the final energy level, denoted by E sub F. Following the equation E sub I minus E sub F equals H times F, where h represents Planck's constant. This postulate, seemingly simple, provided the crucial link between the discrete nature of atomic spectra and the quantized energy levels of electrons within the atom. It presented a bold concept. From these postulates, Bohr derived the energy levels for hydrogen-like atoms and ions by equating a Coulomb force between the nucleus and the electron to the centripetal force required for circular motion. Bohr calculated the allowed radii for the electron orbits. The potential energy of the electron within the Coulomb field combines with its kinetic energy to yield the total energy of the electron. Through algebraic manipulation and the application of his quantization rule for angular momentum, Bohr arrived at the following expression for the energy levels E sub n equals minus 13.6 electron volts divided by n squared, where n represents the principal quantum number taking integer values 1, 2, 3, and so forth. The negative sign signifies that the electron remains bound to the nucleus. This equation dictates a discrete energy spectrum, contrasting sharply with the continuous energy spectrum expected from classical physics. A pivotal achievement of Bohr's model lies in its derivation of the Rydberg constant from first principles. The Rydberg constant, denoted by R, experimentally measures the inverse wavelength of spectral lines in the hydrogen atom spectrum. Bohr demonstrated that his theoretical framework accurately predicted its value. When an electron transitions from an initial energy level with quantum number n sub I to a final energy level with quantum number n sub f, the emitted photon possesses a wavelength lambda given by 1 over lambda equals r times 1 over n sub f squared minus 1 over n sub I squared. Bohr calculated the theoretical value of the Rydberg constant to be r equals m sub e times e to the fourth power divided by 8 times epsilon 0 squared times h cubed times c, where m sub e represents the electron mass, e the elementary charge, epsilon 0 the permittivity of free space, h Planck's constant, and c the speed of light. This purely theoretical calculation yielded a value of 10,974,000 per meter, in extremely close agreement with the experimentally determined value of 10,973,730 per meter. A minor difference existed. This achievement provided strong evidence in support of the quantization of electron orbits and energy levels. Bohr's model addressed the problem of atomic stability. Classical electromagnetism predicted that an electron orbiting a nucleus should continuously radiate energy. This loss of energy would cause the electron to spiral into the nucleus, rendering atoms unstable and unable to exist for any appreciable amount of time. Bohr's postulates circumvented this issue by asserting that electrons in stationary states did not radiate energy. Despite their acceleration, radiation only occurred during transitions between these allowed states. This assumption, though seemingly ad hoc, stabilized the atom. Earlier experimental verification further supported Bohr's predictions. Experiments on the ionization potential of atoms, which represent the energy required to remove an electron from an atom, aligned closely with Bohr's calculated energy levels. The Frank-Hertz experiment, conducted in 1914, provided direct evidence for the existence of discrete energy levels within atoms. By bombarding mercury atoms with electrons of controlled kinetic energy, Frank and Hertz observed that only electrons with sufficient energy to excite the mercury atoms to a higher energy level were able to transfer energy to the atoms. This resulted in distinct drops in the measured electron current at specific energy values, corresponding to the energy differences between the quantized energy levels in mercury. This confirmed the existence of quantized energy levels and transitions. The model saw immediate extensions and applications. Sommerfeld extended Bohr's model to include elliptical orbits, introducing a second quantum number to account for the shape of the electron's orbit. This refined the model and explained the fine structure observed in atomic spectra. While Bohr's model achieved considerable success with hydrogen-like atoms and ions thus possessing only one electron, it encountered limitations while applied to more complex atoms with multiple electrons. The interactions between electrons proved difficult to handle within the framework. Bohr's 1913 paper profoundly influenced subsequent scientific developments. Sommerfeld's extension to elliptical orbits built directly on Bohr's foundational ideas. Heisenberg and Schrödinger's subsequent development of quantum mechanics establish a more complete and accurate description of atomic structure and behavior. Modern quantum mechanics retains the core concepts: energy quantization, stationary states, and quantum transitions. Bohr's model stands as a foundational step. It initiated the development of quantum mechanics. Its limitations are now well recognized. It established key concepts. Energy quantization, stationary states, and quantum transitions are enduring. It laid the groundwork for the development of more sophisticated quantum theories. Bohr's postulates broke with classical physics. Bohr's model transformed our understanding of the atom. It ushered in the quantum revolution. The Bohr model achieved long-term legacy. It serves as a crucial stepping stone. Modern atomic theory and quantum mechanics built upon it. Theoretical models advance scientific knowledge. Superseded models maintain importance.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.